Welcome back to Geometry, Measurement, and Probability. In this video, we pick up in section 11.2 with triangles and quadrilaterals, so let's get started. We have several different types of triangles. A right triangle has a right angle. In an acute triangle, all the angles are acute. Remember, acute means less than 90 degrees. In an obtuse triangle, we have one obtuse angle. Remember, an obtuse angle is an angle that measures between 90 and 180 degrees. A scalene triangle has no congruent sides. We know the triangle to the right is scalene because none of the markings are the same on the three sides of the triangle. An isosceles triangle has at least two congruent sides. Notice the same marking on those two congruent sides. And an equilateral triangle has three congruent sides. Notice the hash mark on each side that shows that the sides are congruent. A trapezoid is a quadrilateral that has at least one pair of parallel sides. A kite is a quadrilateral that has two adjacent sides congruent and then the other two adjacent sides congruent. Now we do have a special type of trapezoid called an isosceles trapezoid. This is a trapezoid whose base angles are congruent. In a parallelogram, opposite sides are parallel. A rectangle is a special type of parallelogram that has right angles. All four angles in a rectangle are right angles. A rhombus is a parallelogram in which all four sides are congruent. A square is a rectangle that has all four sides congruent. All squares are rectangles, but not all rectangles are squares. Also, all squares are rhombi, but not all rhombi are squares. Now, let's move and talk about symmetry. One type of symmetry that we have is called line symmetry. Now remember, symmetry means it's the same. So here, notice in figure A, we have three different lines of symmetry. Each of these three lines divides our figure in half. Figure B has only one line of symmetry, as well as figure D. Now look at the star in figure C. As I start counting, I'll notice that there are 7 different lines of symmetry in figure C. Look at example 1. How many lines of symmetry does each drawing have? We start in part A with a hexagon. Now notice I can draw a line across the hexagon from vertex to vertex, and there are 3 lines of symmetry that go through the vertices. I can also draw lines through the middle of each of our sides of this hexagon, and I have lines of symmetry. So this one has 6 lines of symmetry. In part B, we have the letter A, which has only 1 line of symmetry. In part C, we have an oval. An oval has 2 lines of symmetry. In part D, we have a Z, and a Z has no lines of symmetry. Another type of symmetry that we look at in geometry is called rotational or turn symmetry. We have rotational symmetry when we can rotate a figure less than 360 degrees and we end up matching the original figure. We use 360 degrees because there's 360 degrees in a circle. Now look at the figure on the left. This one says that we have 120 degrees of rotational symmetry. Here's how we get this. Typically, but not always, you can look at how many vertices there are. There are 360 degrees in a circle divided by 3 vertices here is how we get the 120 degrees. Now what this means is I can rotate this figure 120 degrees. My figure looks the same. I can also rotate this figure any multiple of 120, such as 240 degrees, and my figure looks the same. Another multiple of 120 would be 360, but we've come back to our starting point. Now look at the figure on the right. This one also has 120 degrees of turn symmetry. We have 360 degrees divided by 3 different leaves here gives us 120 degrees. So if I rotate this figure 120 degrees, my figure looks the same. If I rotate it another 120 degrees, a multiple of 120, 240, my figure looks the same. And if I were to add 120 or rotate another 120 degrees, my figure is back to my starting point. In example 2, we are asked to determine the amount of turn for the rotational symmetries of each figure. Look at part A. Again, typically, although not always, we can count the number of vertices. This figure seems to be the same at each of the vertices. So 360 degrees divided by 3 gives us 120 degrees. That means I can rotate this figure 120 degrees or any multiple of 120, 240, my figure will look the same. If I add another 120 degrees of rotation, I'm back to 360, which is where I started. Notice that part B has only 180 degrees of rotational symmetry. Now look at part C. Count your vertices here. We have 360 divided by 6 vertices gives us 60 degrees of turn for our rotational symmetry. So I can rotate this figure 60 degrees and it looks the same. I can also rotate this figure any multiple of 60, such as 120, 180, 240, or 300, and my figure looks the same. The next multiple of 60 would be 360, which brings us back to where we started. Our last topic in this section is point symmetry, and any figure that has rotational symmetry of 180 degrees also is said to have point symmetry.